Welcome to this second session on Introduction to Spectroscopy. In this session, I will take up the nature of matter and its interaction with radiation. So, that is a kind of domain I am going to talk about, and the session has been planned as follows. I will begin with a review of what we did in the previous session. Thereafter, we will try to recall, not exactly talk about, because we know about it already, the nature of atoms and molecules. We just recall from what we learned in the quantum mechanical aspect of things. Thereafter, we will talk about the possible types of interaction between radiation and matter, and then we will try to deliberate on the prerequisites for interaction of radiation and matter, and thereafter towards the end we will try to sum up what we do today. Okay. So, let us make a beginning by recalling what we did in the previous session. In the previous session, we defined spectroscopy and outlined its scope and significance. That is the first thing we did there. Thereafter, we discussed the wave mechanical and quantum nature of electromagnetic radiation. Thirdly, we explained the characteristics of EM radiation and emphasized the interrelationships between them. And then we discussed the electromagnetic spectrum and its different regions. So, that is what we broadly covered in the previous session. Now, let us take up what we want to do today. We want to talk about nature of matter. Issue is, why are we talking about nature of matter? You would recall from the previous session that we defined spectroscopy to be an interaction of radiation and matter. What we did in the previous session was we focused on to what is radiation. So, we had different aspects of radiation. Now, I want to talk about the nature part. What is the nature of matter now? So, we have talked about radiation, talking about matter now, then we talk about the interaction between the two. So, that is how we go about. Now, this is, as I just mentioned earlier also, that this is more of a recall, because from our earlier understanding of quantum mechanical nature of atoms and molecule, we know that atoms and molecules have got unique set of quantized energy states available to them. We are very familiar with them, but still we will try to recall them here. So, what do we have is, you will recall that in case of atoms, what do we have? We have, there is an atom, there is a nucleus there, and there are different energy levels over there. This is more of a kind of a model which is little simplistic, because but easy to communicate, because we know that in today's understanding we have what is called as a quantum mechanical model, and what I am trying to depict here is more of a picture which pertains to the Bohr's model, but it is simplistic one, easy to convey. So, I am trying to use that expression, that kind of a picture. And then what we also know is that amongst these energy levels there can be transitions. We will talk more about it as we proceed. So, we know that there are excitations, there could be emissions. If you go from a lower level to higher level, there is excitation. If you come from a higher level to a lower level, that means the electron is at a higher level, comes down to lower level, and it emits a radiation in the process. So, there are two kind of possibilities. We will elaborate on this as we proceed further. Then, in case of molecules, because electrons are slightly simpler systems, because what you have is, you have a nucleus and different the electrons are there in different energy levels. When you come to molecules, molecule is a little more complex, in sense that molecule has got variety of energies. The first one is the translation energy, where the molecule is moving. So, what is the energy for translation? Then there are electronic energy, the different electron energy level there. Then the molecule also is vibrating. So, there is vibration energy component, and then as well there is a rotational component of molecular energy. So, energy of a molecule essentially is made up of 4 components: the translation energy, electronic energy, vibration energy, and rotational energy. And what we have learnt to an extent from our quantum mechanical component, I mean that kind of our understanding of elementary quantum mechanics, that the rotational, vibrational, and electronic states of molecules are quantized. What it means is, in case of electrons we have got only, in case of atoms we have got only electronic energy quantization, whereas in case of molecules we have got quantization of electronic energy, vibration energy, as well as rotational energy. So, the energy level diagram is going to be little more involved, and that is something like this. What do we have is that in a molecule, what you find, there are electronic energy levels. So, this is the ground electronic energy level, then excited state over there. And within electronic energy level, you can see that these lines here are the vibration energy levels. Similarly, here also there are different vibration energy levels, and within vibration energy level we got rotation. These red lines are indicating different rotation energy levels. What does it mean? What does it mean is very pertinent here, is that in case of molecules there are three types of energies which are quantized: electronic energies, rotational energies and vibration energy. But what is important is the difference in energy levels, the order of difference is very different. Electronic energy levels are far apart, vibration energy are relatively closer, microwave energy levels are still closer. What you can see here in the diagram, that the microwave energy levels are quite closely packed, that is, in the rotational energy levels are very closely packed, and the vibration energy levels are about 1000 times larger in magnitude, because this picture is not up to scale. What it shows is that we suppose one of these levels, so first level to second level, these red lines here, so it is of the order of about say 5 to 10 centimeter inverse, or maybe 1 or 2 centimeter inverse to be more correct. Now, we will find that the vibration energy levels will be about 2000, 3000 centimeter inverse, and electronic energy levels will be about 10 to the power 6. So, that is a kind of order of magnitude difference in them. We will, because this has a very significant consequence, that is called as Born-Oppenheimer approximation. We will talk about more about it when we go further into other spectroscopic methods. But right now, let us continue and then see one more point I want to make here before we proceed, that is, we had 4 types of energies and I have just talked about quantization of 3 of them. The translation energy is not quantized, and we are also not interested, because we are not interested in knowing where the molecule is. What we are interested in knowing is what are the electronic energy levels, what are the vibration energy levels, and so on and so forth. We will talk more about it as we proceed. Now, the next issue which we want to take up now is, so basically what we have done is, in the previous session we talked about what is electromagnetic radiation, and now we have briefly recalled what is the nature of matter. Now, we come to the more pertinent part of spectroscopy, that is what happens when a radiation and matter interact. That means, what kind of interactions are possible and what are the consequences of that. Let us see. Now, when radiation and matter interact, there are 3 possibilities. The first one is absorption, emission, and third is the scattering. Those are 3 possibilities. Let us look at each one of them. Now, what basically absorption means is, now suppose a suitable photon, that means when the radiation is coming, radiation has a suitable photon, suitable will qualify a little later, that is, when that photon comes and interacts with matter, it may cause a change. That means, the molecule may go from a lower energy level to a higher energy level. So, by absorbing this photon, that means what happens is something of this kind. The system is at a level E1, that is a ground state or lower energy state. Photon comes, interacts with this, imparts energy to the molecule absorbs energy and goes up to the level E2 of higher energy. That is basically the meaning of absorption. Now, what is a suitable photon? Suitable photon is the one which has got energy exactly equal to the difference in the energy levels, that means the energies of the 2 levels there. That means, this transition from level E1 to E2 can take place if and only if the photon has got energy equal to delta E. In the absence of that, this transition will not take place. So, that is the meaning of suitable photon. Okay. Now, this energy, I am talking in general here, the levels could be electronic. So, if it is electronic energy level transition, we will be talking about UV visible spectroscopy. If it is vibrational transition, we are basically referring to IR spectroscopy. If it is a rotational transition or rotational energy levels are involved, I am talking about microwave spectroscopy or rotational spectroscopy. Now, as against what happens in case of molecules, in case of atoms, things are slightly different off, because you will recall that in case of atoms, we have only electronic energy levels. So, I am just trying to show you a little complicated diagram, which is basically an energy level diagram for sodium atom. So, and all these lines here, the arrows going up and coming down, they basically are trying to talk about the possible transitions, because in case of atoms, we have transition only amongst different electronic energy levels. So, this is in contrast to whatever case in the molecules. In case of molecules, you can have electronic, you can have vibrational, you can have rotational energy levels transitions. But we will not be talking about more about electronic transitions in atoms, because that is not in the purview of this course we are talking about, because our focus is primarily onto molecular spectroscopy. So, we will focus more on molecular spectroscopy rather than atomic spectroscopy. Now, we come back to the molecules. Now, so we just mentioned about 3 kind of transitions. Let us try to go a little more into this. So, what we just saw was that the 3 types of quantized transitions can occur on absorption depending on the energy of the radiation. Let me talk a little more over here. What basically I am trying to see is that let us try to visualize a molecule. The molecule is rotating, it is vibrating, and also has got its own electronic energy levels there. And I just mentioned that the rotational energy, that means the rotational the requirement of energy for the rotation of molecule is a very low type. That means you need very small amount of energy for molecule to rotate, whereas vibration involves much larger amount of energy and electronic energy levels are farther apart. Okay. So, this has to be kept in mind. Now, when I am trying to take a matter, some atom or some molecule, I am trying to shine some light on this. Now, this will interact, that means the radiation will interact with matter, and the kind of consequence will depend on what is the nature of radiation, that means what is the energy of radiation. Because if it is of very low energy, say microwave energy, then what can happen is it can only perturb the rotational motion of molecules, it can do nothing to the vibrational motion, and also the electronic energy levels will not be altered much. Okay. So, that is actually a consequence of your Born Oppenheimer approximation I just mentioned earlier. Let us try to have a closer look at it. Now, suppose I am trying to use microwave radiation and make it interact with a molecule. What can happen is, I just said that it can cause only the transition amongst the rotational energy levels, because microwave radiation has got very low energy. So, that energy is just sufficient to cause change in the rotational energy levels. Okay. And this forms the basis of rotational or microwave spectroscopy, which we will be talking about in the sessions to follow. Second possibility is, if I am using infrared radiation or IR radiation. IR radiations have got energy much larger than that of the microwaves. So, what can happen is that IR radiations will be causing transition among the vibration energy levels, which are farther apart as compared to the microwave or the rotational energy levels. That is the first thing will happen. But in case of infrared radiation, these vibration transitions are accompanied by rotational transitions also, because when a larger change is taking place, there could be small changes. We will talk as we proceed further. These vibrational transitions are accompanied by rotational transitions. That means, the larger transitions are also accompanied by the smaller rotational transitions. We will talk more about it when we talk in detail about the vibration energy level transitions or IR spectroscopy. And these two kind of transitions which take place, they form the basis of IR or vibrational spectroscopy. And third possibility is that suppose I am using ultraviolet or visible radiation, that is of still higher energy. So, that is what we discussed when we talked about EM radiation. That was the significance of talking about electromagnetic spectrum. That means, this UV or visible radiation have got energy much larger than that of the infrared. As a consequence, what happens is they cause transition amongst the electronic energy levels of the molecules, and these electronic transitions are accompanied by the vibrational transitions, which in turn are accompanied by the rotational transition. So, electronic spectra are little more complex, microwave spectra are very simple, vibration spectrum are slightly complicated because of the presence of microwave rotational transitions along with the vibration transition. And in case of electronic transition, I have got electronic transitions accompanied by vibration transition as well as rotational transition. So, a detailed analysis of UV visible spectrum normally is not taken up, but is quite involved. And this forms the base, this interaction forms the basis of UV visible spectroscopy. Now, this is what actually I was trying to refer to. This is a picture which we saw earlier also. So, if you recall that this is my electronic ground state. Within electronic ground state, that means the lowermost energy of the molecule, electronically speaking. Within electronic ground state, we find that there are different vibration energy levels, V is equal to 0, V is equal to 1, V is equal to 2, and so on. So, different quantum numbers are there. And within, say, V is equal to 0, we find that there are number of rotational energy levels. Say V1 also has got number of rotational energy levels, and so on. So, each one of them has got different rotational energy levels. Now, when you have this kind of scenario, and if I am trying to use microwave radiation, so what you will observe is, in case of microwaves, when the energy is very small, it can only cause transition among the rotational energy levels. So, that is what will all happen, nothing else will change. So, this will lead to a rotational spectrum or a microwave spectrum. If I am using IR radiation, what can happen is, I can start from electronic ground state, and then when I go up, I can go up to maybe any of these rotational energy levels. When I go along any of these rotational energy levels, I will be getting absorbing different kind of radiations, and that is what exactly we mean by this. That is, we are going from V is equal to 0 to V is equal to 1 level, but rotationally there are different transitions possible there. That is meant when I said that it is accompanied by rotational transition. Let us go further. If I am trying to use UV and visible radiation, or UV or visible, not and, but then what happens is I go from electronic ground state to electronic excited state, and within excited state also there are same kind of distribution here, the different vibration energy levels, and within vibration energy levels there are rotational energy levels. So, when this happens, so I go from here ground electronic state to excited electronic state, I am finding that I can go to this vibrational energy level, or this one, or this one, or this one. So, this is a vibrational transition accompanying electronic transition, and within this also this vibration transition can reach out to any of the rotational energy levels. So, that is a rotational fine structure coming there. So, that is the kind of picture we have. That means, when I am trying to interact radiation with a molecule, what all possibilities are there? I am talking only about 3 kinds of radiation: microwave, infrared, and ultraviolet and visible. Okay. Now, there are other types of spectra also, but their mechanism is different, because we are trying to focus primarily onto molecular spectra, and that too which are coming as, say, absorption or emission kind of a thing. There are other spectra, say in case of radio frequency, I can do NMR or ESR spectra, but for NMR spectra to be observed, we need magnetic field. Even for ESR, we need enormous amount of magnetic field. So, there are different kind of spectra. So, what I am trying to just talk about is microwave, then infrared, and visible and UV. So, this portion of the spectrum I am trying to, because that is what is where it forms a part of our this curriculum. This other spectra goes beyond it. So, NMR etc. are there, but they are not the part of this course. And then similarly, we got photoelectron spectroscopy or even Moser-Baer spectroscopy. So, they all involve different kind of, because in any case the bottom line is that in all such a spectroscopy there are transition among the energy levels, but what are the energy levels and under what condition do we get the energy levels, that they happen to be different in these cases. So, we will not talk about that. We will focus ourselves only on to this part of the spectrum, starting from the ultraviolet, say up to microwave. So, that is the region we talk about. So, what we have done so far is we have talked about the absorption spectrum, absorption molecular spectrum. Let us see how do we look at the emission spectrum. Before I proceed, let me make a small mention here, that though I am talking about interaction of radiation and matter, radiation is but one way of making excitation in the molecule. The molecules can be excited in a number of ways. Let us see. One is typical absorption of radiation. Second is sometimes we do it by bombardment with electrons or some other elementary particles. The third way of doing that is, that means we put a high potential, that also can make the molecule get excited, or maybe sometimes we do it with a spark, arc, or a flame. I am sure that you have done some kind of salt analysis. When you do a flame test, essentially what is happening there is, though it is an atomic spectroscopy. So, the atoms are in the excited state because of energy from the flame. Then they come down, they relax down, they give energy, that is emission spectrum, that is atomic emission spectrum. So, basically I just wanted to make a point here that the species can be excited by number of possible ways. Absorption of radiation is one of them. So, what happens in case of emission is that a molecule has got excited, that molecule is unstable. So, it will try to come down to ground state, and in the process it emits a suitable photon. Photon will be of energy which will be equal to a difference in energy. Suppose the molecule is at higher level here, when it comes down, say this level is 120 units, some arbitrary units, this is 107. So, when it comes down from 120 to 17, it will give out a photon of equivalent to 30 units of energy. So, that is what it meant by suitable photon. That means that will be equivalent to the delta E. Now, that is the way we can visualize this. So, what you see is that this bunch of lines here is representing E naught, the electronic ground state. As we just discussed some time back, that when I do an excitation, the molecule from this electronic ground state can go on to any of the excited states here. This is excited state 1, that electronically excited state, but it can go into any of the vibration energy levels. When it is there, then what happens is it just undergoes some kind of a small changes there, that means it loses some energy in terms of collisions and all, then comes down to ground state and then comes down as an emission there. That means, from this level it comes down to any of these levels over there. Okay. So, that is a kind of emission spectrum we have. So, in case of absorption we go from a lower level to higher level, in case of an emission we come from a higher level to a lower level. So, that is what basically as an emission spectrum. The third possibility, you recall that we talked about 3 kinds of interaction. The third possibility is, that is when a radiation interacts with matter. The third part of that is, one is we had absorption, second is emission, third is scattering. Let us have a look at it. So, what happens is, suppose this is a absorbing material here, some light is falling on that, the part of the light gets through, it just gets transmitted, nothing happens to that. Part of it gets absorbed, we just talked about absorption spectrum, and then some of that gets reflected back as well. That means, from the compartment of the sample, some light will get reflected back, and some part will get scattered in all possible directions. It is this scattered light what is being talked about when we talk about scattered radiation, which can be made use of to determine the nature of the material which is scattering that. Okay. And typically, in case of scattered radiation, we try to measure it in a direction perpendicular to, because we can't measure it here, because it is a transmitted light. We can't measure it here, we can't measure it here, we can measure somewhere here only, but it is only the scattered light component. We will talk more about it when we talk about Raman spectroscopy. Now, typically this scattered radiation which comes up has got different kind of frequencies. One is called as the Rayleigh scattering. Basically, what happens is, there is a material here, radiation is coming of certain frequency and it gets scattered. Scattered radiation also got the same frequency as this one, that is called as a Rayleigh scattering. That is a major component of scattered radiation. And some of the components happen to be of energy different from the incident frequency. Suppose this is 100 units, this may be 99 or 101. Okay. So, the scattered radiation which is of frequencies different from what we have in case of the incident radiation is called as Raman scattering, and this kind of scattering forms the basis for Raman spectroscopy. We will talk more about it in one of the sessions later on. So, what have we achieved so far? We have talked about interaction of radiation with matter, and we have seen the 3 possibilities: absorption, the different ways of it, there is emission, we know that there is excitation followed by emission, and third is the scattering part. Now, let us take up that is there any requirement, can it so happen that any kind of radiation can interact with any kind of matter, or something more is required? That means, are there any some kind of prerequisites for a reaction for an interaction of radiation and matter? Let us have a look at it. Let us raise this question: can any type of radiation interact with any molecule? The answer is no, because it is not that any kind of radiation can cause any kind of change in a given molecule, because there has to be some kind of a prerequisite. What does it mean? Let us try to elaborate on that. That means, the molecule with which the radiation is going to interact must meet certain prerequisites called as a necessary conditions to be able to interact with a given type of radiation. Let us take up the necessary conditions for interaction of radiation and matter. Let me take the example of microwave radiation. Now, suppose I have a molecule here and a microwave radiation is coming, and we want to see whether it is going to interact or not. What we mean by interaction is it going to cause any change in this, or whether it is going to get absorbed or not. That is a basic meaning of this. To gauge that, what we have to understand is, we know that this microwave radiation is a very low energy, and at best what it can do is, it can only alter the rotational motion, because molecule is rotating, vibrating, and there are electron energy levels there. So, between this, microwave radiation can only cause some kind of a change into the rotational energy of the molecule, that is all it can do. But for that to happen, there has to be some kind of a mechanism between by which the molecule and the radiation can interact, and that mechanism happens to be that if I look at say this molecule of hydrogen, the 2 hydrogen atoms, it is a non-polar molecule. Okay. And on the other hand, I am trying to show a HCl molecule, this is a hydrogen atom, this is a chlorine atom. So, we will see it is a polar molecule. Between the two, what we find that hydrogen molecule does not absorb microwave radiation, but HCl does. Why does this happen so? Let us see. What does happen is that if I have a molecule of HCl, which is a polar molecule, or any other polar molecule for that matter, if that is rotating, then what can happen is, now let us look at this molecule of HCl. So, there is a dipole moment in this direction. Okay. So, when this molecule is rotating, when it rotates, it changes the dipole moment. As a consequence, it generates some kind of an oscillatory dipole moment. Now, since the molecule is rotating, it is generating some kind of oscillatory dipole moment. So, this oscillation is of a given frequency or an order, and when the radiation which is coming there, this and this, the two can match. When the two match, there is a mechanism available by which this radiation can absorb or get absorbed by the molecule. Then we find that the molecule undergoes a transition. That means, if it is rotating a certain this thing, it starts rotating faster, it absorbs energy. But if I look at hydrogen molecule you rotate it in any possible way, there is no dipole moment at all, because dipole moment is 0, it is a non-polar molecule. So, a rotating molecule of hydrogen is not generating any kind of oscillating dipole moment, so it cannot absorb. So, our prerequisite for microwave radiation to be absorbed is that the molecule must generate an oscillating dipole moment in the process of rotation. So, that is a kind of prerequisite we have for microwave spectra or rotation spectra to be observed. Let us take second case. Let us take the issue of say a vibrating molecule. Look at a vibrating molecule. Now, suppose I have a vibrating molecule, and here again what I need to have is that it must accompany some kind of a dipole moment change. Let us take an example here. This is a little elaborate case I am talking about. I am talking about carbon dioxide. Carbon dioxide molecule, this is carbon atom and these two are oxygen atoms here. Carbon dioxide, there is a carbon here, there are two oxygens. It can undergo variety of vibrational modes. So, what you find is say this is an asymmetric stretching. We will talk more about it in the vibration spectroscopy, but since it has come here, I just try to make you understand a little of it. Now, if this is undergoing what is called an asymmetric stretching, that means this is carbon, this is oxygen, this is second oxygen. Suppose this bond is contracting and this bond is expanding, that is what is happening there. That is the meaning of asymmetric stretching. On the other hand, suppose this is my carbon, oxygen 1, oxygen 2. So, both the bonds are contracting, both the bonds are expanding, this is symmetric stretching, or this is carbon in between. So, I can have this is bending mode, okay, or we can have bending like this. So, what you find is that between these there is one mode which is going to be inactive in IR. That means, if I am talking about symmetric stretching, so carbon atom, carbon oxygen dipole, carbon oxygen dipole, the two are in the opposite direction, they cancel each other. So, when it contracts or expands, it does not give any dipole moment. So, in symmetric stretching, there is no dipole moment generation there. So, this mode of vibration will not be the one which will absorb radiation, whereas rest of them are IR active. That means, they are the ones which will be absorbing radiation and they will be showing up in the spectrum there. We will talk more about it when we talk about vibration spectrum. Okay. So, basically here again we have a requirement that the vibrating molecule must be accompanied by an oscillating dipole moment, else IR radiation will not be absorbed, because there is no mechanism available by which the radiation and the molecule can interact. Thirdly, if I have to observe Raman spectrum, for Raman spectrum there is a very special kind of a requirement that the molecule must be anisotropically polarizable. That means, it must be polarizable to different extent in different directions. Let us understand the meaning of this. Let me suppose this I am talking about a hydrogen molecule. So, in case of a hydrogen molecule, we find that the two hydrogen atoms are overlapping, they form a molecule like this. Now, if I am trying to look at hydrogen molecule, if I am trying to put some kind of a field here, so the kind of electron distribution is such that the extent of polarization which can take place in this direction and in this direction happen to be different. Since hydrogen molecule is anisotropically polarizable, it is going to interact with the radiation and give you the Raman effect or give you the Raman spectra. So, okay. So, there again what I am trying to basically point out here is that for any kind of spectrum to be observed, there is some kind of a prerequisite. There something must happen to the molecule such that it provides a mechanism by which the radiation can interact with the molecule and the energy can be absorbed or emitted or whatever. So, that is what we wanted to bring home. So, let us see what we have done today. What we have done today is that we have discussed the nature of atoms and molecules in terms of their quantized energy levels. Atom energy levels are only electronic energy levels. In case of molecules, we have got electronic energy levels, vibration energy levels and rotation energy levels. Thereafter, we talked about different types of interactions possible between the radiation and matter, that is basically absorption, emission and things like that, and we discussed the prerequisites or the necessary conditions for the interaction of radiation and matter to take place. That means, there has to be some kind of a mechanism by which the radiation can be absorbed by matter, and then we can have some kind of a consequence of that happening. Now, in the next session now, what we will do is, because we have been talking about what is radiation, because we defined spectroscopy to be interaction of radiation and matter. So, we have talked about what is radiation, we talked about what is matter, we also talked about possible types of interaction. Now, we will take up in the next session what exactly happens as a consequence of this interaction. How do we talk about that? What do we talk about is in terms of a spectrum. Now, we will try to understand what is the meaning of a spectrum, what are different types of spectra, what are the characteristics of a spectrum, and how can we, what is the significance of the kind of spectra we will be obtaining. So, that is all what we are going to talk about in the next session. Thank you.